So, imagine a universe that is infinitely large. Put yourself in the middle of it. You're going to be watching that object being born. Scientists have discovered a massive void in the universe, and we are in the middle of it. In 1981, scientists discovered that about 80% of the observable universe is full of voids. It's just an empty stretch of nothingness, and we are living right in the center of one such stretch. Beyond that, this nothingness is expanding at an increasing rate and could rip the universe apart. What is this void? Where did it come from? And why is it growing by the hour? Join us in this video as we look at how scientists found the largest void in the universe and how we're smack in the middle of it. During the late 1970s and early 1980s, there was a lot of focus from many astronomers on conducting what is known as redshift surveys of galaxies. A redshift survey is used to measure the extent to which the light from a galaxy shifts toward the red end of the spectrum. In simple terms, it is a measure of how fast something is moving away from Earth. Due to the way our universe is expanding, the farther away a galaxy is, the faster it moves, meaning redshift can be used to measure distance. Also, by mapping the positions and distances of many galaxies, astronomers would be able to create a three-dimensional map of the universe and understand the distribution of galaxies on large scales. This was something Robert Kirshner and his colleagues at the University of Michigan, Paul Schechter, Augustus Oemler, and Stephen Schechtman were working on in 1981 when they discovered what is now called the Boötes Void. Robert Kirshner and his team were working on a redshift survey focusing on a specific region of the sky in the constellation Boötes. They were using telescopes to collect spectral data from galaxies, determining their redshifts and consequently their distances from Earth. But as they plotted the positions of the galaxies, they noticed an unusually large and nearly empty region. This area, which later became known as the Boötes Void, was observed to contain very few galaxies compared to the surrounding regions. The void spanned an estimated diameter of about 250 to 330 million light-years. At first, the team was perplexed as the results of the data did not make any sense. They later analyzed the distribution of galaxies within the void and its surroundings to ensure that the observed emptiness was not due to observational bias or incomplete data. Their analysis confirmed that the void was a real, significant feature of the universe and not an artifact of their survey methods. Later that year, Kirshner and his colleagues published their findings in a paper titled A Survey of the Boötes Void in the Astrophysical Journal. This publication went into the details about the methods used in their survey. The discovery of the Boötes Void, and its implications for the understanding of the universe's large-scale structure. Following the discovery, further surveys and studies were conducted to map other voids and understand their properties. Also, advances in telescope technology and data collection methods, such as the Sloan Digital Sky Survey (SDSS), have allowed astronomers to create more detailed maps of the universe and study voids like the Boötes Void in greater depth. Now that you've gotten a summary of the introduction, let's delve into the matter properly. When you zoom out from your room, house, street, city, state, or country into extremely large scales like solar systems, stellar clusters, and even galaxies, you will notice an interesting and surprising pattern, a web, specifically the cosmic web. Sounds like something straight out of a Marvel movie, right? When you zoom out that far, so far that entire galaxies, each one home to hundreds of billions of stars, are just single dots of light, you'll discover that all you can see is a web. Long, thin ropes of galaxies millions of light-years long and then dense, compact, massive knots of thousands of galaxies known as galaxy clusters. The cosmic web is the largest pattern found in nature. It completely fills the universe. It's an immense, vast, almost overbearing structure, yet it appears as fragile and delicate as strands of pure silk. And sitting among the lattice works of the web, between the walls and knots and filaments, are the great cosmic voids like our Boötes Void? With these voids stretching anywhere from tens to hundreds of millions of light-years across, these are the true deserts of the universe, almost entirely devoid of matter. This means that, judging purely on volume, most of our universe is simply nothing. And as you'll come to see later in this video, this nothing can be very powerful. The Boötes Void was discovered to be about 700 million light-years from Earth. That's really far. Given the void's diameter of about 330 million light-years, our galaxy would fit into it billions of times over. Initially, the region was referred to as the Great Nothing, but later came to be known as the Boötes Void as it appears to lie in the constellation of Boötes, the herdsman who drives the plow around the North Pole. Since this discovery, surveys have managed to create more detailed maps of our universe. As previously mentioned, we now know that galaxies are arranged like a giant web, with the threads being long lines of galaxies. However, between these threads are huge empty voids with hardly any galaxies at all. The voids are said to make up around 80% of the observable universe, and most are around 30 to 300 million light-years wide. Our dear Boötes is one of the largest, earning it the title of supervoid. It's thought that Boötes is the product of smaller voids merging together. To understand this, let's go back to the very beginning of all things. A long time ago, about 13.8 billion years before now, there was no cosmic web. There were no galaxies and no stars. There were just the fundamental components of the universe: dark matter, hydrogen, helium, and a little sprinkling of lithium for flavor. In fact, it is said that all the universe's fundamental components were tightly packed together initially. This is thought to have been a uniform soup or store-bought milk, pretty much evenly spread throughout the universe. But gradually, there began to develop random quantum fluctuations here and there, leading to differences in the distribution of matter. Some areas were now slightly more dense than others, meaning their gravitational pull was greater, and they pulled matter away from the less dense areas. This made them even more dense, increasing their gravitational pull again, so they attracted more matter, and so on. Then, slowly but surely, over the course of hundreds of millions of years, the denser regions got denser. Small clumps of matter flowed into the dense pockets, where it eventually formed into the first stars, galaxies, and clusters. Since the coalescing matter had to leave somewhere, their region of origin soon became void. As the cosmic web grew and evolved, however, while these regions are referred to as voids, they aren't entirely empty. There are still some dim, scattered dwarf galaxies floating around in these mostly empty areas, and dark matter and some hydrogen have also managed to cling to life inside these cosmic and celestial deserts. But by and large, the voids really are mostly void. And because of this voidness, ironically, the voids are filled with one thing: dark energy. The term dark energy is used to describe the phenomenon of the universe's accelerated expansion, as well as the unknown force responsible for it. While the nature of dark energy remains uncertain, the most plausible hypothesis suggested by scientists states that it is closely linked to the vacuum of spacetime. Now, dark energy appears to be present wherever there is a vacuum. Technically, the room you are currently in contains dark energy, as it is present in the small voids between and within atoms. However, dark energy possesses a relatively weak force, which makes it susceptible to being masked by the mere existence of almost anything else, such as matter, radiation, or even mundane objects like dirty socks in the corner. Now, you don't get to experience or directly perceive dark energy because of the abundance of matter in your environment. However, the emptiness of these voids means that these areas are exactly where dark energy gets to play. Interestingly, the phenomenon responsible for the accelerated expansion in our universe occurs within the voids themselves. As these voids exert physical pressure on their surroundings, they drive apart the galaxies and dissolve the great cosmic web that took billions of years to construct. As such, to understand these voids, we must be able to wrap our heads around the concept of dark energy. Quite literally, we must stare into the void. So, what is dark energy? Dark energy is a hypothetical form of energy that is proposed by physicists to explain why the universe is expanding at an accelerating rate. It is the dominating form of energy in the cosmos, driving the accelerating expansion of the universe, and remains elusive and mysterious for scientists. Think of dark energy as the evil counterpart to gravity, an anti-gravity force providing a negative pressure that fills the universe and distorts the fabric of spacetime. As opposed to the gravitational attraction that dark matter exerts, dark energy accelerates the separation of cosmic objects. Dark energy is estimated to account for around 68% to 72% of the universe's total energy and matter, meaning it heavily dominates both dark matter and everyday matter. Currently, the only real answer to the question, what is dark energy, is we don't know, even though it might sound very unsatisfactory. However, scientists are not entirely unaware of the situation. A number of candidates have been put forward to explain dark energy. These include the vacuum energy of space, which involves particles literally popping in and out of existence in empty space. Then there is the theory of a fifth force that is responsible for the negative pressure that might cause the accelerated expansion of the universe. There are several alternative flavors of fields that may be considered to explain dark energy, including fields of tachyons, which are fictitious particles that travel faster than light and thus back in time, and a low-energy field referred to as quintessence, among other concepts. However, all of these remain purely speculative, meaning that the only way we can really know dark energy is through its impact on the universe. Now, why do scientists think that dark energy is a necessary part of the universe? About 25 years ago, it was concluded that the universe is expanding, and not just that, but that the expansion is speeding up with time. This process was discovered to have been happening for the last 5,000 million years, and it was causing galaxies to recede from others. Although all our cosmological observations back up this phenomenon, scientists still need an explanation for this trend in the expansion. However, what they do know is the properties of the ingredient that causes this effect. It has to be a substance or fluid that overcomes the attractive nature of gravity, and it has to be diluted and spread in all spacetime. In 1999, physicist Michael Turner used the term dark energy to refer to the hypothetical component of the cosmic budget. This naming was essential as it provided a credible rationale for the ongoing pattern of the universe's expansion. In the absence of it, the rate of expansion would decrease, leading to the ultimate collapse of the universe and causing a reduction in the distance between galaxies within the large-scale structure. This is very important to note. You see, our cosmological model predicts an expanding universe, and as a consequence, the existence of an event that scientists call the Big Bang. However, the current state of the expansion is not constant in time, instead, it is increasing. This means that this growing rate in the expansion has to be driven by a different factor, something that wasn't predominantly acting during the early stages of the universe or at times when galaxies formed. However, because scientists can't measure it directly and don't even know what it is made of, formulating experiments to detect it and study its very nature becomes really challenging. Now, according to the vast majority of observations, the most likely candidate for dark energy is the cosmological constant, often related to the fluctuations of the quantum vacuum. It is also the preferred and most simple explanation for dark energy to the point that it is included in the standard cosmological model. But there are other candidates, such as scalar fields, Galileans, axions, tachyonic fields, or even dynamical dark energy models. Now, what really does dark energy do or not do? If dark energy is causing the universe to expand at an accelerating rate, shouldn't we see our coffee mug shift away from us or notice our commute to work getting longer each day? We don't typically observe phenomena like this because objects bound by gravity, such as stars, planetary systems, star clusters, galaxies, and even our coffee cups and tables, appear immune to dark energy's influence. Gravity remains the dominant force at smaller scales. However, dark energy seems to exert its influence on the vast expanse of the universe, driving the expansion of the cosmos. This phenomenon can only be observed by studying galaxies and other celestial objects separated by massive distances of millions, billions, and even tens of billions of light-years. The greater the distance between these celestial objects, the more rapidly they move away from each other. To illustrate this concept, imagine marking 3 points on a deflated balloon, with 2 close together and the third farther away. In this analogy, dark energy is like the air inflating the balloon, overcoming gravity's pull. As the balloon expands, all 3 points move away from each other, but the farthest point moves more rapidly. Similarly, 3 galaxies with one farther away will move away from each other, with the farthest galaxy moving faster due to the stretching of space between them, much like the balloon's rubber skin. However, as they separate, galaxies retain their shape and don't spread apart internally, thanks to another dark aspect of the universe known as dark matter. Although both have similar names, dark energy and dark matter are more different than alike. While both are referred to as the dark aspect of the universe and both are mysterious and defy explanation, dark energy isn't the energy equivalent of dark matter. Their similarities end with the quality of being directly undetected, and we can infer their existence by the effect they have on visible matter. Dark matter is a hypothetical form of matter that doesn't emit, absorb, or reflect radiation, making it invisible. Dark matter is therefore literally dark, thus the prefix dark is used more literally in dark matter than in dark energy, rather than alluding to a mysterious nature alone. The main way we know dark matter exists is from its gravitational effect of holding galaxies together. Without the gravitational influence of dark matter, galaxies would swirl so rapidly that the gravitational influence of their visible matter, stars, planets, gas, and dust, would be insufficient to prevent them from flying apart. What does this mean? As dark energy is pushing things apart on a large scale, dark matter is holding galaxies together on a smaller scale. In that respect, dark energy and dark matter could almost be considered as having opposite effects in the universe. The universe appears to be the rope in a cosmic tug-of-war between dark energy and gravity, with dark matter as the primary rival with the greatest pull on the side of gravity. But what is the true muscle content of dark matter? In terms of the energy and matter content of the universe, we've seen that dark energy accounts for an estimated 68% to 72%. That leaves around 28% to 32% of the universe's matter and energy budget for everything else, which are mainly dark matter and baryonic matter. According to CERN, the European Organization for Nuclear Research, dark matter outweighs baryonic matter in the universe by a ratio of about 6:1. That means around 25% of this energy matter budget is dark matter. This therefore means that the matter that composes stars, planets, and everything we see around us is no more than 5% of the universe's total contents. This is why solving the mystery of the dark universe has become a pressing concern for scientists, as its existence means we literally have no idea what around 95% of the universe is. Having said all this about its form and influence, what evidence do we have for dark energy? The first detection of dark energy through the discovery that the expansion of the universe is accelerating was made by two teams of scientists working independently in the late 1990s. These teams were conducting surveys of type Ia supernovae, which are cosmic explosions that occur when massive stars die, producing light emissions so uniform that they are excellent for measuring cosmic distances. This is because, as the universe expands, light from distant sources that takes a long time to travel to Earth has its wavelength stretched out as red, a color associated with long-wave light. This results in a reddening of light that astronomers call redshift. The further away a light source is, the more its light is redshifted, with light from extremely distant sources that existed when the universe was young shifted into the infrared region of the electromagnetic spectrum. The astronomers were observing these supernovae to attempt to measure the rate of universal expansion, called the Hubble constant. What they found was that more distant supernovae that had exploded when the universe was much younger were fainter than expected. This meant these supernovae were farther away than they should be, implying the expansion of the universe was speeding up. This discovery would be confirmed with follow-up observations and by measurements of a field of radiation left over from just after the Big Bang called the cosmic microwave background, CMB. The discovery of the redshift of light from distant sources, and thus the expansion of the universe, by famous astronomer Edwin Hubble in the 1930s forced Albert Einstein to drop a factor from his equations called the cosmological constant, represented by the Greek letter lambda. Going back to our swing scenario, the onset of this second bout of expansion is as if suddenly. Without the application of a further push, the swing in our analogy is moving faster and reaching greater heights, appearing to defy gravity. What dark energy is doing to the fabric of spacetime in this dark energy-dominated period of the universe is analogous to that phantom push. Now, if you're worried about what happens to the child on the swing as it speeds up in our analogy, think how worried cosmologists must be about what dark energy means for the fate of the universe. Thus, understanding dark energy is key to building an accurate model of how the universe has evolved over time, which includes the shape it takes and how it will end. Both the origin and fate of the universe are determined by its critical density, which the Swinburne Center for Astrophysics and Supercomputing defines as the average density of matter required for the universe to just halt its expansion, but only after an infinite time. If the matter or energy density of the universe is equal to the critical density, then in terms of geometry, the universe is flat, like a sheet of paper. Now, in a matter-dominated universe, the critical density is between the density required by a collapsing heavy universe and the density of a light universe that expands forever. The total content of the universe without dark energy is only around 30% of what is needed for a flat universe, which is the type of geometry the universe should have if created by the Big Bang. This is because early inflation should have smoothed out the universe geometrically like a sheet of paper. The addition of dark energy to the universe's mass energy budget tops it up enough for the universe to be flat, and in the simplest models of cosmic inflation, it brings the density of the universe close to the critical density. Before the introduction of dark energy, cosmologists had assumed that eventually, the attractive influence of gravity would overwhelm the expansion of the universe. This could lead to a few possible ends for the universe, such as the Big Crunch, which suggested the universe would begin to contract and draw in on itself. The acceleration of the universe's expansion dispels this idea. If dark energy continues to accelerate the expansion of the universe, then rather than a big crunch, its fate could be a big rip. This is a scenario in which dark energy eventually becomes dominant over every one of the universe's fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces. This would mean breaking or ripping apart everything that is currently bound together by those forces, be it galaxies, planets, or people, even the protons and neutrons that make up atoms. While you're considering the importance of these dark energy facts and the possible consequences of the accelerating expansion of the universe, remember that it all started with this gigantic void that makes up the majority of our universe. Thanks for watching another episode of Space Trailway. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.